I think we have been planning for quite some time to do this webinar. Yeah. So can you all hear me? So I'm audible, right? So okay,
Yes, you.
fine.
Yes,
Yeah. Okay, then I think we have been discussing for quite some time to do a webinar like this for the benefit of the student community. So I was listening to the number that he told. I mean, around 30 to 40,000 students from Kerala, migrating to the countries outside in terms, seeking better opportunities. Yeah, I see, it as a more encouraging number because in the sense that, we gain our knowledge only by going and visiting places and understanding, especially in the technology field, right? We go outside, we see, we try to go to the places where there is better practices of technology, and we try to, improve our knowledge and understanding of the world. And that's a good sign. That's how I see it. And I tried to let's make it a, if you guys are interested, we make it an informal discussion. I have just tried to put together some slides, and which I thought could be, it's at a very basic level. In this short presentation, right, we will just, this is the topic that I have chosen, opportunities, sources. My domain experience is in semicon, so I will just focus on that area. And let's see, based on your questions, we can discuss further too. So the semiconductor market revenue, right, worldwide. So this is where it all started, roughly, I would say. I mean, it was way back even before that. But then let's put a timeline because that's when we saw these exponential growth in semiconductor industry. So you could say it's from 1987 to 2024. It's we started seeing all these revolutions alongside computing and software. So you can see from a meager less than 50 billion US dollars, how it has gone up to $600 billion. It's a sort of, you can see a parabolic curve, right? Almost a parabolic curve with some ups and downs. So this is a very significant growth for any industry, just like the software. So why it is significant is because, it generates so much of revenue. And that means it it started from something pretty simple, and then it started going into very complicated domains, and it started touching every aspect of our life. I don't want to go into detail in all this, you all know. So how it evolved. So now at 2023 it's at 500 to 600 billion dollar. That's what they say. Now in another 10 years this growth can double, and it can go to a $1 trillion economy. So this is what is predicted by the analysts. So it's around a CAGR of 7.1%. You can ignore all these intrinsic, extrinsic material and buy node size and all these, comments. But important point here is the region. So where do we see all these growth? You can see the North America, you can see Europe, Asia Pacific, and then you also have South America. I mean, obviously India will also be there. I mean, partly because of our government policy has changed in the last couple of years. We understood that semicon is the next oil, and in a positive direction, we are making, some steps so that we can at least catch the not the last bus, at least the remaining bus in this growth story. We actually missed in the 1990s a big opportunity to set up all these semiconductor business. If that was the case, I mean, India would have been a completely different economic situation, compared to as it is now. So yeah, anyway, it's up to the leadership of the country to determine which track we want to, and the vision of the leaders, of course, and also collaborating with different regions of the world where we can get the best designs, get the best technical know-how. And this is what actually determines, if you see any nation, you take Taiwan, you take South Korea, everybody cooperated at the right point of time with the regions in the world where there was a lot of innovation happening. And this resulted in an exponential growth of the economy of these countries. So I would rather say that we are in at a late stage to catch this bus, but still we are hopeful. So just like the IT industry, right? We also started at the back end of operations of the semicon, and then slowly we moved into design. And we are at a phase where, we have our own talent in this field. So see, what is mainly important here is this number, that is dollar 990, or is a $1 trillion out of our economy, right? This is what we should concentrate on. That means there is a lot of opportunity for a lot of people in terms of jobs, in terms of setting up startups, in terms of setting up, companies, and then, generating revenue out of it. So maybe some of you or all of you already know that, the first integrated circuit, this is like a 10 mm by 10 mm. That's what Jack Kilby was able to produce as a bipolar device that you see in the left corner here. And then the first monolithic two-dimensional integrated circuit, it was from Robert Noyce. You can see this, the chip itself here. And from there, we are in a situation where we have, FinFETs in terms of vertical stacking of these devices. I don't want to go into these details. If anyone of you like to know more about all these, evolutions and what point we are in terms of analog design, you can contact me offline. I will be more than happy to help you out. So you can see so this is one transistor. Now on a 300 mm wafer, you can see that you have millions of these small devices. So we know in the college we have this Intel 8080, right? So this had around a density of 300 transistor per mm square. And deep learning engines, what we see nowadays, have 25 into 10 raised to 6 transistor per mm square in 16 nanometer CMOS technology. And so this is the sort of growth that we have achieved in terms of semiconductor, and then that is resulting in these massive changes that we see in the lives of people. And literally, semicon is going to touch in the years to come each and every aspect of human life. And this is something for technically, if you are interested, this is where we started. So you can see the gate length of the CMOS that is starting around 500. And then in 2020, it is going to almost a nil. We are at 1 or 2 nanometer size. And I can see, when I started the design, that's way back in 2003, I started at the 350 nanometer node. And now, because I'm in the analog domain, it scales a little bit slower because it's a little bit complicated than purely designing a digital front ends. It has reached a level of probably around 25 nanometer or 45 nanometer. We are not able to scale because of the technical complexities associated with the design. But nevertheless, this is how it is reaching, and it reaches to a point where, what's next? And that's very exciting phase of semicon. And the next decade, right, we will see a lot of path-breaking technology in terms of process and also in terms of, all the design aspects, especially with the recent surge in AI. We will see all these culminating in a lot of job opportunities. But then getting into this semiconductor domain, I would say there is a sort of an entry barrier. And often in the recruiting stage, we find that the skill set that is required is missing in the right set of candidates, even though they are graduating from very top tier universities. So that's it. Next slide. I was just trying to summarize all through these couple of years that I worked in the industry, whatever job profiles that I saw. So we know that any phone or the semicon, it is based on a memory, right? It's a starting point. So for the memory, you can see that memory design engineers, memory validation engineers, these are the starting points. Then progressing up, you will have IP leads. Then you have the memory system principal engineers who are at the pretty senior level. Then you have design managers who manage the different aspects of the project execution. Then you also have layout engineers. And when we say layout, right, it's actually the mask that we need to do before it actually goes for the production. And This also has opportunities for growing up to IP layout leads and principal IP engineer layout. This is 10 plus years or 15 years plus experience. And then we have the digital, which is for SOC integration or digital signal processing, which also involves physical design. So when we start the design, we start at the behavioral level, the RTL level, which needs to be synthesized at this millions of gate level. Then if you look at the DSP, that function is also embedded into the RTL side of this. And then that also everything needs to be synthesized basically at the physical level to the silicon. So we need design engineers, which we call as front-end design engineers, analog front-end, digital front-end, and then you have digital back-end. And then we have the CPU design engineers. So it's again trying to optimize the performance of CPU unit. Then we also have functional modeling engineers. We need validation engineers. For example, we have the huge complicated SOCs or the PMU. So the power management units interacts with the CPU side. For example, when you turn on the phone, you need to do a lot of, you start up with a lot of functions, and then you need to validate all the interface of the digital with the analog. In a mobile phone, if you see, you have a mix of both, right? You have the analog side where you have these RF antennas, then you have the battery side, you have a battery management circuit, and then you have the linear power management circuits. This is constantly handshaking with the digital side of things. And then you have the digital backend, and where you have the physical, the PD group, then you have the static timing analysis, you need to do the synthesis, gate level, and then you need to extract, it goes to the fab, and all these process. And at the senior level, where we end up is as digital architects. I mean, we have IP leads for all these codecs or audio functions that we realize at the RTL level. And then again, design managers who will actually manage the whole team. Then at the analog level, it is at the most, I would say, in the whole process, it requires a lot of intuition work to design. And we say, if you see the job boards, right, they will say as in analog design engineer for ADC, for PLL, for DDR, memory, analog, mixed signal design, PMIX, RF design. It's a lot of domain there. And you will also probably see some designers who have spent their lifetime doing one aspect of it. So for example, if you take the RF design, right, it's there will be designers who spend their lifetime in that, or you take SerDes. That's also a very promising area. So it's a skill set where overlapping is rarely possible. Sometimes, yes, because of the product complexity, you will be expert in different domains. And as I said, the next ladder will be the analog IP leads, and then we go to the analog chip architects who have years of experience designing these sort of systems. It starts from principal engineer and above, which requires almost like 12 plus years of experience in the industry. And we also have analog system architects, in the sense when we go and meet a customer, we need to basically talk with them in the language of technology in terms of analog or digital. So then we have these system architects who will talk mainly about the system that we are going to design. Then at the other side, these are all like the memory, digital, and the analog side. These are all the main functional aspects of the chip design. Now, once the chip comes out, we have something called the reliability design. So we are packaging the chip sometimes to, the chip package itself. And that itself is a complicated art. You need a package design engineer there. Then you have the noise coming into picture. So you need a EMC design engineer role. Then we have the ESD, which is related to the electrostatic discharge. And we need a specialized skill set, simulation environments for that. So all these are like, different domains. And once the product is designed, we have something called as application design. So what we do in the application design is that, from the chip level, you migrate to a board level. So the previous iPhone, board that I showed, you will have to validate their whole system piece by piece in a PCB. And then we will have to make it production ready with the ATE setup. So then we have the PCB design engineer. We also have the application system level designers who will make the product, and also at the technology side we will have the with experience hardware architects. Then we also have test engineering, and so this is another thing. I mean, so in the whole memory, digital, and the analog designers, at the architect level, it's continuously back and forth with test engineering, because that result, test engineering will tell us which part is qualified to go into the production and which is not going into the production. So that will also result in these post silicon validation engineers, ATE engineers who will set up all the ATE measurements. Yeah. So and then the whole thing also work on the tools, right? So we need CAD support. So we have EDA tool support engineers. We have with the knowledge of Perl, Skill, and Python. Yeah. So I've just tried to put two sentences. What is the way to get into this field? I mean, get enough work experiences in India. I mean, India is such, as I said, I mean, at the semicon level, we are doing very good. And some of the pay levels in the recent years have, I would say, it is almost matching the European standards. So that is also another thing to be, if you are specific that you want to work in India itself, the growth trajectories will be a little bit slow, but then when it starts going and you get enough experience, right, the pay levels are nowadays matching what you can get abroad minus the bonus part. And there is, if you are looking for, since this seminar is, for applying abroad, once you get enough experience, right, we can start applying abroad. There are headhunters. You can move your CVs through LinkedIn. It all works. And then, and there is another path, as you all know. You can do the Master of Science abroad and apply for job abroad itself. So these are the ways in which normally we try to seek an opportunity overseas. So the university-wise, the American university system, you all know. You can target top 30 universities. I wouldn't say this is good, this is bad, nothing like that. The fundamentally, what are the interview points or something we look at is what is the basic knowledge level. So what is the knowledge level for example, in the semicon, it is at the circuit theory. If you're looking at the mechanical engineering side, or if you're looking at the civil engineering side, once you do a Master of Science, right, we always look at at the entry level, we will look at the how strong the fundamentals are, and that's very important. And after that, once we get enough experience, right, the shift moves away from what university we have graduated. It will actually move towards the experience and the projects that you have gained. And the interview will last only for the work that we have done. And then when we come to UK, you can target top 10 universities for triple E courses. And there are courses in MSc, MSc is for 1 year, MNG is for 2 years. Normally, it is the TOEFL MNG route. So this is, you need to write TOEFL, and based on your marks in the final semester, they will form a short list. But the important point is in UK, right? They basically, they don't have many ways to evaluate candidates. So they will look at your TOEFL score. They will look at your final year semester scores, and obviously they may look at universities if we come from the universities that they have heard of or their alumni have come out. Yeah? So this makes a difference. For example, the committee may have some connection to the alumni of the colleges where you have completed, and then they will look at it. Oh, okay, we have a guy who is applying now from this particular university. So let's see his grades and offer a place. I mean, in USA, you can see that I would just say it's a mecca for technology. I don't have any other words to say. So the top 30 universities, it as good as that's the best. Then you come to UK, you have top 10 universities. which are also at the same par. Some of them in as in the colleges in the US, but we mainly try to focus on the top 10 universities. Then in the coming to Europe, the in Netherlands, this is what I could see from the candidates there: University of Twente, University of Utrecht, Rotterdam, Delft, Maastricht, Eindhoven. In the net, I see that it is direct application and they have their own entry criteria. Partly, I think it is determined by the number of candidates applying per year. So they will have their own criteria, which is evaluated based on, I think it's based on the grades and what you present in the CV finally. And in Sweden, you have the Lund University, Uppsala, Chalmers, KTH, Linköping. In our firms, we have people who have graduated from these sort of universities. In Belgium, the KU Leuven has a very nice group for chip design. And in Belgium, you have the University of Ghent. In Switzerland, obviously the EZTH. So that's EZTH is also one university where a lot of high caliber guys join. And then there is also St. Gallen, EPFL. And coming to Germany, so yeah, RWTH Aachen, that is one nice university, especially for computer science graduates. I have interacted with some of them, and I have found that they have been well trained. And we have for the microelectronics Karlsruhe, then TU Munich, and there is also Faculty of Sciences Erlangen, which is probably on the system side of design. TU Dortmund, there is also Rhein-Ruhr University, there is TU Berlin. And if you go to PhD level, you have to go obtain it from Fraunhofer institutes. They have a microelectronics path. They have a scientific path. I think it's with some other institute. This Fraunhofer is for the core engineering side of it. Yes, we need to know German at the C1 level. That's pretty important if you apply for a university in Germany. So that's the starting point, but they have some courses in English also, which are taught in English. And yes, so one of my favorite quotes: the way to get started is to quit talking and begin doing.